Welcome to the Control Engineering webcast, Advanced Process Control, Past, Present, and Future. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering and CFE Media and Technology. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RCEP at rcep.net. A certificate of completion will be issued to each participant. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RCEP. The course description for this Advanced Process Control webcast is shown here and on the webcast registration page. I won't read it, so we have time for more questions at the end. Learning objectives on the next slide explain what we will cover. Learning objectives are to define Advanced Process Control, APC, terminology, review APC tools available today, understand single loop control, multi-loop control, and the matrix, learn to identify APC opportunities and select appropriate solutions, understand process optimization, compare costs, benefits, and limitations of APC tools, impart a shared working knowledge of APC to all stakeholders, apply insights from the past, present, and future to overcome today's challenges, and review APC 2.0 future trends. To get the best results from the webcast platform, please make note of the following as you participate in today's event. If you're having technical problems, click on the question mark at the top right-hand corner of the screen to bring up a list of system checks to make before escalating to an online technician. If you are experiencing issues with your slides or audio, please refresh your browser or click the Refresh Media button directly under the presenter's headshot. You can control the volume settings of this webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you need a technician, type a message into the Ask a Question box and someone will get to you as quickly as possible. Answers to your technical questions will be in the Answered Questions box on the left side of your screen. You can use the Ask a Question box on the left side of your screen to type questions for the speaker during the presentation for the Q&A session at the end. You may ask questions at any time during the presentation, and we'll get to as many as time allows. Questions for today's presenter will be answered verbally during the Q&A session at the end. To download the presentation slides, use the Event Resources area on the left side of your screen. To take the Learning Unit exam, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a new browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. The exam will be posted with an on-demand version of the webcast. The exam is for 1 RCEP ACEC Certified Professional Development Hour. The webcast is being recorded, including the Q&A session. We'll post the archive on the Control Engineering website in a few days, and we'll send you an email with a link to the archive once it's ready. Method of delivery and category. This event is a live educational webcast presented on January 9, 2020. An educational category is Technical, Health, and Safety. We welcome to the webcast Alan Kern, the owner of APC Performance, LLC. He has more than 30 years of advanced process control, APC, experience and has authored numerous papers on cost-effective APC solutions. He's the inventor of a patented Rate Predictive Control, RPC, industry's only inherently adaptive control algorithm, and of XMC, industry's only model-less method of multivariable control. He is a 1981 chemical engineering graduate of the University of Wyoming and has a professional engineering license in control system engineering and in chemical engineering. I'm moderator, Mark T. Hosky, Control Engineering Content Manager. Alan, please go ahead.
Okay. Thank you, Mark, for the introduction, and hello to everyone. I'm Alan Kern, the owner of APC Performance. I'm presenting today from Phoenix, Arizona. These are today's continuing education learning objectives, as Mark mentioned. This webcast is a somewhat ambitious idea, the past, present, and future of APC. But ultimately, I think we put together a pretty good mix of introductory, advanced, and insightful topics. The overall objective is a high-level review of today's APC landscape, highlighting some of the most important aspects of that landscape going forward. Another strategy employed is to identify gray areas on the APC landscape and drill down to see how they are likely to play out as a way of gaining insight to what we can expect in the future for APC. And here's why this is important and timely and why we wanted to do this webcast. So I need to explain one thing, which is that we were unable to use any web-sourced artwork in this public presentation. So you'll have to bear with me on some of these redacted images, and I hope your imagination can fill in. So regarding this missing image of the iconic 2001 Space Odyssey monolith, I want to say that the APC landscape today could be described as monolithic. For some time, it has been dominated by Model Predictive Control, or MPC. Industry has spent a lot of unplanned resources on MPC since the 1980s, so that other aspects of APC have gone underdeveloped in the computer age. But APC is essentially the robotics of the process industries. It's where we do value-added automation. And really, we cannot afford for progress to stall for years on end. APC in all its forms must evolve into an on-site core competency of the process industries if we are to successfully meet the challenges of the automation age that we live in. This presentation will focus mainly on the underdeveloped aspects of APC and some of the gray or problem areas, because that's where I see activity, changes, and progress coming in the 2020s. But I do want to acknowledge the reigning king of APC, which is MPC. MPC is pretty well known in industry at this point. It's a big technology, it's a good technology, it's demanding, and it's expensive. Nonetheless, industry has given MPC a big thumbs up over several decades, because MPC has also been the technology to bring some million-dollar paybacks, sometimes with ROIs as short as a few months. The main trade-offs are high cost, lengthy deployment, and high maintenance, which have all proven to be stubborn problems. Overcoming these, or getting around these, is one of the main issues facing APC today. So the first order of business is to sort out some of the admittedly often confusing APC acronyms. One good way to frame advanced process control is in contrast to its counterpart, basic process control. The basic process control system is typically a DCS or PLC system that facilitates safe plant startup and operation, but does not typically address advanced control. The BPCS is an integral part of initial plant design and construction, since it is essential to plant operation. Advanced process control is an umbrella term that refers to all types of APC collectively. There is both single-loop APC and multi-loop APC, which we'll talk about. APC is typically added after plant commissioning, sometimes many years later, and often piecemeal, to capture operational efficiency and optimization opportunities or overcome operating problems that become evident in the course of operation. A question that's often been asked is, how can APC be included in initial plant design in order to capture APC benefits from the beginning? This presentation will shed some light on one way that could happen. MISO and MIMO terminology has been adopted fairly widely in print, so it's good to know. But it's not usually used informally in conversation. MISO, multiple input, single output, is more commonly known as ARC, Advanced Regulatory Control. MIMO, multiple input, multiple output, is commonly known as multivariable control. I have divided this into two parts, conventional MPC and multi-loop control, or MLC. The term MLC is adopted here to meet two needs. One is to provide a technology-independent term for MIMO control, or for multivariable control, and the other is to refer to the middle region of the APC matrix spectrum. So here's how this terminology falls in terms of APC matrix dimensions. Matrix size is the number of manipulated variables by the number of controlled variables. A 1-by-1 matrix would be a single loop controller, such as a PID loop. Anything greater than that, involving more inputs or more outputs, would be some form of APC. Here is how the CISO, MISO, MIMO terminology falls on the matrix spectrum. And here is the most common terminology, which I'll use going forward. Except MLC, or multi-loop control, is used as a technology-independent term for multivariable control, roughly in this matrix size range. MLC also represents an APC tool gap. That is, few tools have yet emerged for APC applications in this matrix size range. I would say this is because industry expected MPC to naturally expand into the MLC region, but that never happened. MPC costs of ownerships remain high, and MPC remains primarily a high-end solution. So MLC, this blue region, represents an important but decidedly underdeveloped part of the APC matrix spectrum. This table then is a summary of these three main areas of APC: advanced regulatory control, multi-loop control, and model predictive control. A series of continuing education webcasts is being considered for the future to focus in greater depth on each of these in turn. I want to take a moment here to answer a good question that was submitted already at registration time, which asks if APC includes batch control. The answer is technically yes, but not today. According to Wikipedia, APC is an umbrella term covering a broad range of techniques and technologies, including specialties like batch control, compressor control, inferentials, etc. However, for today's presentation, I'm again taking the more mainstream or conversational usage, which is that when most people think of APC, they think of continuous multi-loop control. So a complete process control timeline might include dozens of milestones and more than 100 years of progress, but for today's purposes, I've just got a few that I want to mention or need to mention. You could say that Ziegler-Nichols in 1942 began the era of detailed loop analysis and precision calculated controller tuning. But until the 1980s, process control remained almost exclusively a single loop discipline. The control systems technology to do automatic multi-loop control, for the most part, simply didn't exist yet. That doesn't mean that processes didn't have multi-loop control. It means that operators had to do it manually. That's an important distinction in understanding the role of multi-loop control in modern process operation today. We'll talk more about that. The situation changed in the 1980s with the rise of computers and methods to implement automatic multi-loop control, in particular model predictive control as first published by Cutler and Ramaker in 1980. Industry went large with MPC, and the rest is history, as they say. The period from 1980 until now could well be called the MPC era, or as I tend to call it, APC 1.0. But the MPC era has also shown that MPC does not provide the more agile, mid-sized multi-loop control tools needed for many applications in the ARC and MLC size range. Going forward in the 2020s, I expect to see industry increasingly address this with the emergence of appropriate tools and APC activity in the ARC and MLC areas. There's an important difference between single-loop APC and multi-loop APC. Single-loop APC strives to improve single-loop performance of important loops. It is typically a loop performance mission. Techniques such as feed-forward or adaptive gain are used to improve performance of a single loop. Multi-loop APC, on the other hand, strives to automatically coordinate multiple individual loops. Like an orchestra, the individual loops are expected to be in tune, and the multi-loop controller serves as the conductor. Multi-loop control is an automation mission. It automates the otherwise manual task of adjusting single-loop controller set points and outputs. What are the implications of a lack or shortage of automatic multi-loop control? It means large portions of process operation remain under open-loop multivariable control. Open-loop control, as we know, is a highly undesirable condition resulting in more alarms, constraint violations, and upsets, and less optimization. In the past, multivariable control has often been treated as something you either have or don't have on a process. But virtually every process operation is an exercise in multivariable control. Ask any board operator. The question is it manual or has it been automated? Is it open loop or is it closed loop? With that said, here are some updated definitions that are important to bear in mind going forward for APC. When an operator makes changes in the course of a shift, set point changes in the course of a shift, that's manual multivariable or multi-loop control. multivariable or multi-loop control automates those actions. By the same token, we can now say that open loop control, which used to mean manually adjusting the output of a single loop controller, we can now say includes manually adjusting set points of controllers that have not been incorporated into an automatic multi-loop controller, but could be. So I feel these definitions are very important because they provide a straightforward, simple, intuitive way to understand APC and its role in industrial process operation. This is something that's definitely been lacking throughout the APC 1.0 era. These definitions, because they're intuitive and easy to understand, put all participants on the same page, not just APC engineers, but operations personnel, process engineers, and managers. With everyone on the same page, we can expect greater APC progress going forward. So many of you will recognize this slide or something like it. This is a time-honored way to illustrate the difference between open loop and closed loop multivariable control, and is worth revisiting with these new definitions in mind. What this says is that with open loop MLC, the operating team has to keep operations safely away from constraints. But this comes with an economic or optimization penalty. This space between the operating region and actual limits or targets represents lost capacity, efficiency, etc. With closed loop MLC, we can safely operate closer to constraints because there is an automatic response should a process change or disturbance occur. With closed loop MLC, you can operate closer to targets and limits because MLC can be relied upon to automatically respond to encroaching constraints, which may occur due to normal process variations. In the same way, more importantly really, MLC can automatically pursue receding constraints to capture yet greater earnings and optimization. So this is a pretty good conceptual way to understand the benefits of open versus closed loop MLC, or multi-loop control. Another thing I want to say about benefits is that they've often been a gray area under APC 1.0. But if we look at APC with these intuitive definitions, simply as automation that closes loops, I think almost everyone understands the intrinsic benefits of closed loops over open loops. And in most cases, we can accept that justification with confidence, especially where the cost of MLC is reasonable. Moving on to the next topic. Why do I say mighty matrix? Let me count the ways. The matrix is perhaps the single biggest contribution to APC technology and process operation to come out of the MPC era, possibly even more so than models. A basic understanding of the matrix is key to a working knowledge of APC. Analyzing a process and diagramming the underlying matrix will become a basic core competency skill going forward for APC engineers and process engineers. The matrix is a simple, elegant way to diagram the multivariable nature of a process. But the matrix concept is not complicated. This slide shows a small process and its matrix. The details of the process are not important here. The main parts of the matrix are these. Along this axis are the MVs, or manipulated variables, which are the single loop controllers being automated. Along the other axis are the CVs, or control variables, which are the related process variables that are to be kept within constraints and optimized to the extent possible. The matrix area itself identifies which MVs affect which CVs for control purposes. These are also referred to as models and may be a detailed dynamic model as an MPC or simply gain direction as shown here. Gain direction is the same concept as single loop control action, direct or reverse. This is the essential information contained in a matrix. It shows how the multivariable nature of the process may be manually managed, and serves as a functional spec for a multi-loop controller should you choose to automate it. So it's a very useful diagram to develop and have on hand, whether it is actually automated or not. In fact, I believe the matrix concept should be migrated beyond the APC space into operator training, DCS graphics, and other areas to help develop a wider shared understanding of the multivariable nature of most process operations and of the role of APC. Okay, I'm just looking at my notes here, and I think my mouse is an old mouse, and it's making it click. So I'm going to move it a little away from the speaker, but I don't know if I can do away with it. So that's the mighty matrix. I wish I could say more and do it more justice. With time, I believe more people will come to see it in this way. So we're covering a lot of ground here, as you can see, but this is past, present, and future of a big topic. Next, I'd like to move on to process optimization. One of the important, or most important, but I think poorly understood gray areas in conventional APC, in an area where I see change coming in the future. This diagram shows how process optimization normally occurs at an operating site. Site-wide production planning, of which optimization is an inherent aspect, utilizes a wide range of information and planning tools to develop optimized production plans. Updated plans are passed down the operating chain of command, typically daily. From there, each unit is responsible for its part of the plan. In practice, this often involves manual actions, such as adjusting equipment. As we know, it can also involve many controller adjustments by board operators, which basically, represent manual open-loop multivariable control. Closed multi-loop control can be used to automate parts of this, potentially capturing significant economic or operational benefits, such as greater consistency and timeliness, fewer alarms and constraint violations, and greater optimization. So this is where APC resides in the scheme of things. It is a tool to automate appropriate aspects of unit optimization, but it should not be confused with overall optimization itself. This is really the only way optimization can work. However, it raises questions about the role of optimizers in the control layer. Conventional MPC, here in the control layer, incorporates its own built-in optimizers. There are actually two optimizers within conventional MPC technology. The first one is the steady-state solution. But what is its role relative to the site-wide production planning solution we saw on the last slide? And aren't optimum operating targets usually well known among the operating team in the first place? So this optimizer appears redundant on a couple scores, even as it contributes to MPC cost and maintenance, second only to model maintenance. The second MPC optimizer maps out MV moves to take the process to the steady-state targets while minimizing error or maximizing profit along the way. But industry has learned in single loop, as well as multi-loop control, that while minimum error may seem like the obvious criteria for control performance in industrial operation, observing safe process speed limits and minimizing overshoot and oscillation normally take precedence over minimizing transient error, so that the move optimizer becomes another large footprint solution to a diminishing and transient part of the problem. For these reasons and others, MPC control layer optimizers don't fit well in the APC big picture going forward, and I expect them to become an obsolete aspect of APC in the future. Another gray area with implications for the future of APC is model maintenance. It turns out that models are predominantly short-lived rather than long-lived as industry originally expected, and this has posed a fundamental problem for model-based control. Model-based control is great technology in theory and has worked well in many applications, so I don't see it going away. But I don't see the model fidelity conundrum being solved either. There are important lessons if you connect these historical dots that suggest industry might have seen this coming and may need to think outside the box and incorporate these lessons to find solutions going forward. Articles with more information about these can be found on Control Engineering online. Looking forward, I see model-based control remaining flat as a high-end niche solution where the maintenance and support requirements can be met and justified, with emerging MLC tools picking up in the gap applications. Let's take a closer look at these MLC gap applications. The first thing I want to emphasize is it's a big gap in the APC toolbox. About the biggest ARC application that can reasonably be done is a 1x3 override. ARC is typically implemented by existing on-site control engineers, so there is little or no cost. It typically takes a few days or weeks and is entirely owned and operated in-house. In comparison, a 10x20 MPC application is actually somewhat small. Many exceed 100 CVs. Cost is often in the hundreds of thousands of dollars. Time frame can be up to a year or more. So this is a huge gap in industry's APC capabilities. As I mentioned, the only reason I think industry has gotten to this point is the user base expected MPC to naturally evolve to fill this gap. But it has been unable to overcome the cost, schedule, and maintenance issues. And increasingly, industry is looking for alternatives to move APC forward. So let's take a closer look at what these MLC applications actually are. It's always been said that there are many automation opportunities in this matrix range, matrix size range, but they fall below the radar of the large MPC paradigm. This chart is effectively a low-altitude radar that reveals these applications. This is a chart of the number of loop interventions in terms of set point mode or output changes at an operator console over a given time period. And these are the 25 worst actors, the loops requiring the greatest number of operator interventions. This is an easy chart to make on any modern DCS console. It's a fair assumption that many or most of these represent manual multivariable control scenarios where operation becomes caught up in frequent micromanagement of groups of related controllers. I think we've all seen that. Moreover, every single intervention represents lost opportunity that had an automatic multi-loop controller been deployed, the moves could have been made in a more timely manner, capturing greater optimization. Not to mention allowing the operator to play a more process oversight role by relieving them of this repetitive task. Maybe this looks familiar to you. Industry has used a similar approach twice in recent memory to bring about industry-wide improvements in alarm management and loops and manual, except now we're talking about multivariable loops and manual. A loop interventions metric like this would tell a lot about the level of automation, how well it is working, remaining automation potential, and serve as a tool to steer progress. Here's how it might work at an actual operating site. With this chart in hand, you may want to follow up on some of the worst actors, or possibly operation has complained about a particular loop. It may turn out to be a standalone issue, which might be an opportunity for single loop APC, or potentially it could be a valve or instrument problem. Next, you may identify 3 related loops that need to be considered together. This can come out of process knowledge, discussion with operators or process engineers, or may be evidenced by highly coincident interventions in the data. This reminds us of the old adage that historical data is rarely useful for modeling because operators tend to make multiple related moves together rather than one move at a time as required for modeling. Further investigation reveals the related process variables whose limits, alarms, or optimizations are triggering the frequent interventions. With variables identified, the matrix can be completed, although obviously this can be a somewhat iterative process. But it's not complicated. It all comes out of basic process operation knowledge and involving the right people, typically operations, process engineers, and control engineers. The completed matrix can then be deployed and automated in the control system using appropriate MLC tools. The entire deployment cycle could take as little as a couple weeks and cost relatively little money where MLC is an on-site core competency. If a variable or model needs to be added or deleted, that is also easy. On the whole, MLC total cost of ownership is probably more like ARC than MPC, thinking back to the gap slide a few minutes ago. So what are the qualities and features industry needs in emerging MLC tools? In a word, agility. The lack of agility, in a word, has been the reason MPC has been unable to absorb these mid-range applications. To be agile, MLC will probably be mainly a feedback control technology and avoid dependence on models and optimizers to the extent possible. Agility is also essential to achieving on-site core competency. On-site means MLC can be owned and operated by on-site control engineers rather than off-site resources. It will enhance agility and core competency if MLC tools can be deployed natively within the BPCS platform rather than as a third-party add-on. These are the basic qualities I'm looking for and expecting to see in emerging MLC tools going forward. Another point to mention is if MLC does not depend on models and can be deployed in the basic process control system, then many APC applications could be included in initial plant design stage. So here's another analogy useful to make 2 points about emerging MLC tools. The analogy, since we don't have the pictures, is that MPC, traditional multivariable control tool, is more like a large commercial oven, while MLC is more like a microwave oven. So I want to make 2 points. The first point is that MLC tools can make all the difference between having and not having automation. Suppose all you need is popcorn. Will you fire up the big oven and summon the chefs? Probably not. With MLC tools, you can meet this need with a more appropriate expenditure of resources and within a more appropriate time frame. Who wants to wait hours for popcorn? Another important way that MLC is like a microwave is that it increases or can increase APC capabilities and resources. The concept of MLC strikes some people as an additional load on already stretched APC resources. But agility means MLC is much easier to own and operate. It makes your automation dollar go farther. And most importantly, it engages more people in the automation effort. So it actually increases resources and capabilities, just like a microwave increases kitchen capabilities. Virtually every kitchen has one. Here is a cost of ownership summary for the 3 main types of APC. ARC is usually carried out primarily by the control engineer to improve performance of a single important or problematic loop. MLC is typically an on-site operating team effort, including operations personnel, process engineers, and control engineers, as well as APC or process specialists. MPC is typically carried out by a project team. I'd like to begin wrapping up by summarizing the future insights that have been mentioned throughout the presentation. I refer to these collectively as APC 2.0. I think industry is about done waiting for MPC to fill the MLC gap, and the future will see the emergence of more agile MLC tools. Industry would probably be well served by adoption of a loop intervention metric as a tool to drive the closure of multivariable loops and manual, just like the loops and manual and bad actor alarm metrics before it. Control layer optimizers and model-based control, as we've come to know them, are both overdue for a reckoning of some sort. The results of that we don't exactly know yet. But in any case, I see MPC flat going forward, both due to continuing maintenance exposure and due to the emergence of alternative MLC tools with increasing interest and activity in the ARC and MLC areas. I see ARC and MLC becoming much more active at the plant level throughout industry, ultimately earning and being recognized as an essential core competency of the process industries. Whether you like to think of APC as the robotics of the process industries, or as an orchestra conductor, or like adding a microwave to your APC kitchen, these trends together have the potential to unlock a new generation of APC progress. Once again, these have been today's webcast learning objectives. Reviewing the list, I think we did some justice to all of these in the limited time available. Overall, I hope this gives the audience some useful information and insight to how the APC landscape may transform in the coming 2020s. Now I need to turn the microphone back over to Mark, although I will remain online for Q&A.
Well, thanks very much, Alan. Now we do have a question and answer session, and the audience listening live can type questions for today's presenter in the Ask a Question box on the screen. We'll answer as many questions as we can, and within a few days, the presentation will be available for on-demand viewing, along with the link to the quiz for potential PDH credit. We'll post the archive on the Control Engineering website, and we'll send you an email message with a link connecting directly to it and to related resources after it's ready. And now on to the questions. So there are many questions about AI, deep learning, IIoT, RTO, that sort of thing. Maybe go over some of that acronym soup and explain what their implications would be for APC.
Okay, I heard that. I'm going to try to keep my answers to a minute or two so we can get some more questions. So let me pick on AI out of that and say that it's not really my area. I see AI as a potential tool to do things faster, not necessarily better. And so what I have seen in the APC or in the multivariable control area is that we've had a very hard time doing successful modeling, as I mentioned, due to the changing nature of the models in the plants. I think we've been, even users and even the people who produce advanced control stuff have been surprised that the plant's not the same from day to day, and there's just a vast array of the types of disturbances that can come in. So we've seen a similar thing with neural nets. They've been a little unreliable, I would say. And even benchmarking studies. At some point in the past, it's hard to find a point now and a point a year or something in the future that makes a valid comparison. So for me, AI is obviously really very important in computers and in all kinds of things going forward. But I don't see it hitting APC in my horizon, you might say. And my horizon doesn't go that far at this point, another 5 or 10 years. So that's all I can say about that.
Thanks, Alan. Please clarify how MLC would do optimization without optimizers.
So the first thing is that optimization occurs at the business level. We shouldn't confuse the idea of optimization down in the APC in the first place, although those waters are very muddy. So optimization occurs at the business level where all the tools and information are available, whereas none of the tools and information are available down there at the control layer, or not much. So at the APC layer, optimization, what it really refers to is how we use excess MV availability or degrees of freedom. So in other words, in that pentagonal slide we saw, the first objective of APC is to get the operating region, within the constraints. And then the second objective is if it's got any leftover MV availability, and it almost always has some, it needs to move that operating point, in an optimal direction. And that's what we mean down at in APC. We mean optimization means how do we utilize remaining MV availability or degrees of freedom? And then the question, how do we do that without an optimizer, is where do those optimization targets come from? And they can come from the business level, from the site-wide production planning. They can come, and usually do come, I think, the great majority of them, from engineers who configure targets and limits based on process design knowledge, from operators who might take the plan passed down from production planning on a daily basis and change things based on feed rates and product grades, etc. So, and on occasion, there needs to be a live calculation for a target, but that's actually quite the exception. So that's how I think we need to understand optimization a little bit differently. It's how we use the MVs, the remaining MV availability. It's not doing the optimization itself down there at the control layer. So that's a good question, though, because it's been a very gray area in APC 1.0.
How does model-less APC work?
Okay, that's a common question for me because we do have an MLC tool that we call model-less multivariable control. It makes a lot of people wonder. Most people assume that means there's AI, in fact, or something intelligent behind the scenes that's sort of making a model as it goes. But it's simpler than that. Basically, model-less control just means feedback. So model-based control, here's something to remember for those people who are maybe more at the introductory level of APC. Model-based control is essentially feed-forward control. And model-less control is essentially feedback control. So I will say that in the course of developing or working on our MLC tools, you mentioned we've patented some algorithms that are especially suitable to the multivariable application. But basically, model-less means feedback. That's the easy way to remember it.
Good, thank you. Let's see. If I don't follow how error minimization is, I don't follow how error minimization is a mistaken assumption, if not error minimization. So I don't understand okay. So yeah, maybe you can explain that a little bit.
Okay, so what I said was that error minimization is almost always the criteria for control loop performance. But if you've been a control engineer as long as I have, you've seen a pattern, which is that a site may embark, maybe they're tired of tuning issues coming up all the time or modeling issues with MPC, and so they embark on a campaign to use some new tools and go out and retune everything. But when that's over, what happens is there's an increase in the fact that you've got to go back and actually detune or retune, or in the case of MPC, dial in some move limits or extend some control times. So the problem is that error minimization is an aggressive criteria, and it leads to a lot of MV movement or fast MV movement and excessive overshoot and oscillation. In industrial process operation, these are the least desirable performance characteristics. It's much more important to get to set point at safe speed and with minimum overshoot and oscillation. So that's the good news, is I think industry's been learning that. But the bad news is this type of performance does not really lend itself to direct measurement or mathematical measurement, but can really only be gleaned by overall metrics such as loops and manual, right? If you have a loops and manual, then maybe something's wrong with your tuning, or multivariable loops and manual, or the number of alarms. So we can only glean optimal tuning or whatever modeling based on our overall reliability and availability. Okay.
Good. Another question. Perhaps you could discuss fuzzy logic and feed-forward control a bit.
So fuzzy logic, it always comes up in the discussion. My career has been long, but I've never used it. But I can say it always comes up in the discussion. So kind of like AI, it's not something I can speak much to. Feed-forward, on the other hand, is a very important topic that and every control engineer should understand how it works. And it's not complicated. Again, if you are a new generation control engineer, you should take a day and understand it. That's all it takes. And one reason it's important is not only because it's a core element, probably one of the best things you can do in single loop APC, but feed-forward is also kind of the equivalent. It's the single loop version of model-based control is how I look at it. It's a valid comparison. So once you understand feed-forward, it'll help you understand multivariable, multi-loop model-based control as well. Hang on, I'm going to say something more about this. Let me think about it. I guess this is it. A lot of times, what I like to say about feed-forward is that if you're missing a feed-forward signal, it'll find you. You don't have to find it. If you've got a disturbance that's really kicking your stuff in a process, and you look at it, you're going to understand feed-forward pretty quickly and what you need to do to implement it. So, and I think in industry in general, we found, especially in single loop control, and I kind of mentioned this on one of the slides earlier, that actually turns out to be not that common. And that's one of the burdens we created for ourselves with MPC is we use 100% models. Not only is model-based control feed-forward, they use it 100%, you might say, at every matrix location. And but that all comes with maintenance. So anyhow, in single loop world, feed-forward applications will find you. And the other thing I wanted to mention on this, it was crossing my mind, that doesn't get a lot of attention is dead time. So dead time is another control technique that everybody should learn in the beginning because you see a lot of that, how it works, what you can do. And basically I'm talking about, a Smith predictor with variable dead time. If you learn how to use that and you learn how to use feed-forward, that's a great start on being a control engineer. Okay.
All right. Thanks so much, Alan, for the Q&A. Let me mention again that the questions that we didn't get to, we'll try to get offline and then attach that to the asset area of the registration site. So thanks again to our presenter, Alan Kern, PE owner and consultant of APC Performance, LLC. And with that, we'll move right along to the close. Now that we're just about done, we want your feedback. A short survey will pop up on the screen as soon as the webcast event ends. Please take a moment to complete it. We use the information to improve our webcasts. Finally, on behalf of Control Engineering and CFE Media and Technology, thanks for attending. This now concludes our webcast. Thank you and goodbye.